Can you hear me? Can you hear me now? Too loud? That's probably good, huh? Keep going, talking a little more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
know how to do this. Hello, everybody. Hi. Welcome to the Sustainable Solutions Seminar for winter term. This term, the speaker series is a collaboration between the School of the Environment, the Institute for Sustainable Solutions, and the Department of Architecture. My name is Martha Works. I'm from the Geography Department, and I'm the professor of record for most of the sections of the class for which this is offered for credit. So this is offered for credit. If you're enrolled for credit, the syllabus is posted on D2L, and I do have a few copies here, but see me after the class if you have any questions. Let's see. We're going to start with just a few introductions, and then we'll go on to the speaker. First, I'd like to introduce John Reuter, who is the acting director of the School of the Environment, who will welcome you, give you the official welcome, and then Spresa Halimi from the Institute for Sustainable Solutions will introduce our speaker. Thank you.
So I actually don't have anything to say. I just wanted to welcome everybody to this this seminar that's co-sponsored by Institute for Sustainable Solutions, the School of the Environment, and the departments, and the Department of Architecture and Fine and Performing Arts. And especially if you're not taking it for credit, welcome. Because, if you are taking it for credit, just chill. You'll get your credit. You just have to, sign up in the right form someplace, and we'll work that all out. But now I'd just like to introduce Spresa from Institute for Sustainable Solutions.
Thank you and welcome. I am Spresa Halimi, Research Assistant Professor with the Institute for Sustainable Solutions and the Instructor of Record for the Architecture 407-507 and the PhD Level 607, ESR 607 course. So come and see me if you have any questions. And my colleague on the back, Carol Franco, is also will be co-instructors for those courses. Before I introduce tonight's speakers, I have a couple of announcements. First, I would like to welcome all the students, community members, as well as viewers online. We are streaming our lectures live online, and we do have an online audience, and they are encouraged and welcome to ask questions. A little bit about the Institute for Sustainable Solutions. We are Portland State's cross-campus initiative for sustainability, advancing integrated research, teaching, and action that leads to solutions for a more livable future. We have just launched a student award program called Solutions Generator, which gives groups of students funds to design and carry out projects that make our campus and community more sustainable. Applications are due by the 20th, and for more information, you can pick up a card from the back table over there, or come and talk to our staff, one of our staff members, after the lecture. We have blocked time for questions and answers after the lecture. Please come up to the microphone. The lecture is being videotaped, so please remember, if you have any questions, to come up at the microphone. Tonight's speaker is Dr. Jana Compton from the Western Ecology Division of U.S. EPA Office of Research and Development in Corvallis. She is a research ecologist focusing on biogeochemistry at US EPA. She received her master's and PhD degrees in forest ecosystems and biogeochemistry at the University of Washington. Prior to joining EPA in 1999, she was a postdoc researcher at the Harvard Forest and assistant professor of soil biogeochemistry at the University of Rhode Island. Her research at EPA focuses on element cycling and biogeochemistry at scales from microbes to the continental US in order to better understand and manage the effects of human actions on water quality and terrestrial and aquatic ecosystems. She currently leads a national project on integrated Management of Reactive Nitrogen in EPA's Sustainable and Healthy Communities Research Program. Please join me in welcoming Dr. Compton.
Hear me okay back there? Thanks very much, Spresa, for that introduction, and to all the previous folks for this great seminar series. I'm really excited to be here. It was fun to think about solutions. As a biogeochemist, we often are thinking about the problem and better understanding the problem, and it's nice to be able to kind of be required to think about solutions. And it's also a good time for us within EPA's research program. We are spending a lot of time thinking about, we know we have a problem with nutrients and nitrogen management, that it's affecting air and water quality, and right now, how do we go about making the best decisions to reduce nitrogen pollution and nutrient pollution for those kinds of improvements. So we've been working on a number of questions related to solutions, and one of the things, I have a person working with me, Holly Campbell, who wasn't able to come along today, but she's been reviewing case studies where we've had successes in nutrient management. And there aren't a lot of places where we've pulled all this information together, and it's been a real interesting to do that, and I'm going to share some of those results with y'all today. So I'm going to talk about just enough of a good thing. Often the nitrogen problem is cast as too much of a good thing. And I think our getting toward a solution is finding just the right amount of a good thing. And I'm at EPA. I'm a research scientist at EPA, so I'm in the research arm of EPA. And I'm pressing buttons, and nothing is happening. Do I need to point it in a certain direction, or? Can go back to the. Okay, thanks. So nitrogen and ecosystem services. We know that nitrogen is a critical component of energy, food, and fiber production. Probably with the green revolution and the introduction of nitrogen fertilizers, people say at least half the population of Earth is sustained by nitrogen fertilizers, and so it benefits humans in many ways, and some of these ways are shown here. We can see over time that this increase in nitrogen is really striking. You see in the early 20s, during the war, nitrogen fertilizer production is a byproduct of munitions development during World War I and World War II. And you see this really ramping up after the 40s and during the Green Revolution. This is nitrogen for the U.S., and here we see the share produced by nitrogen fertilizers, the share from fossil fuel combustion, so that's power plants and cars largely, and then also nitrogen fixation by crops that we plant, in large part to feed animals, but as food. Here, and then this is the natural background, which comes from things like lightning. This little tiny line here is lightning. The natural background also includes nitrogen fixers that you would see that are not cultivated. So red alder is an example here in the Northwest. So there's been a huge change, and probably a 3 to 5-fold change in the amount of reactive nitrogen that's coming out of the atmosphere and going onto land. And this has been cast as a problem that's outside the boundary of sustainability. And this is kind of a relative index of different human actions, biodiversity loss, climate change. This green circle here is meant to represent what's considered to be sustainable. And you can see here that nitrogen, the nitrogen cycle and human activities that have altered the nitrogen cycle are one of these areas that's far outside the bounds of what is considered sustainable. Where is this nitrogen coming from? As I mentioned before, agriculture and fertilizers are a large part of it. here. This is about half of the pie. The natural background fixation is maybe about a quarter of the pie. Industry, which is production of non-fertilizer and plastics and nylon, that's another maybe 20% or so. And then fossil fuel combustion is another quarter of the pie of the increase in reactive nitrogen at the scale of the U.S. This is what's happening at the scale of the U.S. We can also look at this spatially. And where does this nitrogen go? You can see that spatial imprint on the landscape. The red is areas with higher, many more times higher than background. So here the red is 5 to 10 times higher than the natural background. You can see a lot of this is in areas with intensive agriculture, and that's largely what these red areas represent. You can here see the Willamette Valley with our agricultural systems, eastern Washington, the Sacramento Valley. A lot of these are both agriculture and fossil fuel combustion in those areas. But it's kind of an interesting perspective to be able to see the extent to which the U.S. has been altered by, places in the U.S. have been altered by reactive nitrogen. So there's a whole host of things that happen with this increasing nitrogen. There are many sources, and there are many impacts. And this is a list of some of them that have been documented very well by Jim Galloway at the University of Virginia. We have smog and haze, which has a number of impacts on visibility at the national parks, for example. We have forest dieback and acidification that impact pristine lakes and forest ecosystems, especially in high elevation, especially in areas around cities or in the northeastern U.S. Nitrogen also produces nitrous oxide, which is both a greenhouse gas and an ozone-depleting chemical. So it's actually, now that we've got the Kyoto Protocol and we've reduced all of the CFCs from air conditioning and so forth, N2O, nitrous oxide, is actually the highest contributor to the ozone depletion currently. And so the ozone issues are depletion of ozone is one of the other concerns, and then also eutrophication and water quality issues associated with excess nitrogen. So what happens to this nitrogen? And all of that's really been nicely laid out in a concept that's called the nitrogen cascade. The idea is based on decades of biogeochemical research, but really was formalized by Jim Galloway, who I mentioned before at University of Virginia. But it follows this nitrogen from many sources into the many impacts. And so we talked about ozone effects, the particulates and particulate matter and stratospheric ozone effects, the particulate matter affecting haze, and also particles that affect folks that are sensitive, have sensitive respiratory issues, respiratory illness, and asthma. That's a big component. Effects in the agri-ecosystems, which are generally positive. We have increased crop production. That's something that we benefit from. We have effects on forests and grasslands, and then we have surface water, groundwater, and coastal effects, including coastal acidification that interacts to some extent with the nutrients. So there's a whole host of impacts. Getting good data and good quantification on these impacts is part of the story. So the scope of the problem as it affects things that EPA regulates, which is largely air and water issues, we have 14,000 nutrient-related impairment listings in waters of the U.S., and this is probably an understatement since we don't go out and document that in all of them. About 50% have high levels of nitrogen. This also talks about phosphorus. 1/3 of U.S. estuaries are eutrophic, and there's at least 168 hypoxic zones in U.S. waters. This map shows you kind of the spatial imprint of this nitrogen in surface waters. The big black circles are the drinking water standard, and so you can see that there are a number of places where we have nitrate concentrations in surface waters that are above what we think is safe for drinking water, and that standard is based on blue baby syndrome, which is it's largely based on risk of blue baby syndrome, which affects infants and their ability to process oxygen and cycle oxygen in their blood. And so we have areas where we are above that level. You can see some of the hot spots, but they're distributed throughout the country, these higher levels. At lower levels, the nitrogen can also, at lower levels here, we also have effects on algal blooms and coastal productivity as well. The way that we regulate, for the most part, the water, nutrients in water is through the TMDL process, which is the total maximum daily load. And this just shows you the number of TMDLs associated with nutrients in U.S. waters. And so this, if you look at Oregon, we have something on the order of 100 to 300 nutrient-related listings in waters of Oregon. So these are things that are related to nutrients, either algal blooms or pathogens or things that are related. So this shows you, this is kind of the process by which we go about making a change and making decisions about reducing the nitrogen and phosphorus coming into these waters. So we also have eutrophication of coastal waters. These are just some graphic pictures of an algal bloom here. This is the Gulf of Mexico Hypoxia zone. I think this was in 2010, which was a particularly strong year. And so you have large areas of low oxygen. Organisms that can survive in that low oxygen, organisms that can move can get out of the area. And organisms that can't move, a lot of bottom-feeding organisms and crabs and shrimp, those are not going to survive those low oxygen events. So that's a real concern and is motivating some of the nutrient regulation processes. There's a good negative relationship between seagrass beds with more nutrients, and especially nitrogen. You have algae dominating these seagrass beds, and you lose those seagrass beds with high nutrients. And those seagrass beds are host to all kinds of fish and other species that are very important, both recreation and sometimes fisheries production. And so that's a real important change that's happened associated with nutrients. This map shows hypoxic coastal areas worldwide. There's a lot of them in the east, a lot of them in the Gulf, other areas with high human activities and development. We have some in the coast of Oregon and Washington. Some of those are driven by ocean circulation and not so much nutrients. But they're throughout the globe. We are starting to see more and more of these events and areas with hypoxia that we need to be concerned about. And then one other thing that hits a little closer to home, this is violations of nitrate in drinking water. And so since 1998 to 2008, there was about a doubling of nitrate violations, meaning nitrate concentrations that were over the standard, the safe drinking water standard in community water systems. So this is places generally where people are taking groundwater and drinking that water. When that water's tested, it doesn't meet the nitrate standard. And so in my view, that's a real concern if the water that we're drinking is being contaminated to the point where we have to worry about it. And then this is nitrate concentrations in Oregon. So this is from work of Brenda Hoppe at OSU and Oregon Department of Health Science. She's been documenting in Oregon, we're lucky. We have this real estate transaction database where every time you sell a house, you have to measure a few chemicals, and nitrate is one of them. And so she has this record from all of this information. You can see some of the hot spots. And this is that the red and the yellow are 7 and 10, which 7 is the Oregon action level. You can see these hot spots of nitrate in the Willamette Valley. This is in Lapine, where they had some problems with septic water. There's other places in Umatilla that are also called groundwater management areas, where they're going to take action to try to reduce the nitrate. And that's what's happening down here in this groundwater management area in the Southern Valley near Corvallis. So, it's a problem that's happening in many places, and one of them is here in Oregon. So I'm hoping I've given a pretty good scope of the problem. What I want to do now is to shift to talking about the components of the solutions. And it's clear in many, many places, and becoming more clear all the time, that we need to reduce nutrient inputs to air, land, and water. And we need to figure out the best way to do this, the most effective way, cost-effective way, the way that's going to have the least impact on things that we care about. And so we're trying to have a somewhat new approach and a new perspective on dealing with these problems. And some of it involves bringing in the concepts of sustainability and ecosystem services. And so bringing the presenting the issues to decision makers and stakeholders in ways that they can see the impacts on themselves. And we're not necessarily going to be changing the laws that exist, but trying to bring new approaches to these existing solutions. Examination and analysis, one of the things that I'll be talking about today is examination and analysis of successful nutrient management in the U.S. and also in Europe. They've been dealing with these problems for a long time, so there's some good case examples of how they dealt with it in Europe. And I'll talk just a little tiny bit about the role of the individual. So ecosystem services, how many folks in here know what an ecosystem service is, has heard this concept before, has talked about it in a class? So that's good, lots of people, because that's changed over the years. I've been asking this question for 3 or 4 years, and the first couple of years people didn't know, so it's becoming more accepted. The definition that I like is aspects of ecosystems that produce human well-being, that contribute to human well-being. So human health, well-being, all the different components, including economic components. And so for the work that we're doing within EPA's Sustainable Healthy Communities program and all of EPA's sustainability research that we have going right now, the goal is to incorporate into decision-making ideas that represent ecosystems in a way that people appreciate the impact, so that we're able to present things in units that people understand, that the broader public will respond to, and that we make those kind of connections. And that's kind of a new thing. It's more of a social science cooperating more and interacting more with economists and other social scientists to look at these problems. So it is really a new way of thinking for us, and we're just starting down this road. We've been working on this for about 3 years now. So some of it involves what some folks are calling the triple bottom line. I'm not sure if I really like that idea, but in any case, we're talking about ecosystems and environment, we're talking about economics, and we're talking about health and well-being, or the social factors. So it's incorporating these pieces into decision-making. And a lot of our previous decisions and management involves an ecosystem condition, or maybe a nitrate concentration or a nutrient concentration that we think is not acceptable. And then that feeds into decisions and then feeds back into these stressors and drivers. And I think what we're trying to do is incorporate more of the economic valuation, the connection between condition and services, trying to make these connections, and also the impacts on human health and well-being, so that we can present this information when we're talking about alternative decisions or scenarios. So that's kind of the thinking that we're trying to bring in. And one specific problem that EPA has been presented is from our Science Advisory Board. And the question is, if you were to reduce nitrogen by 25%, they're asserting, and this is a 2011 report that came out in September, they're saying we should be able to reduce reactive nitrogen input to the U.S. by 25%. There's a lot of things that we can do. We should be able to do that. What's the most economically efficient, socially acceptable, and environmentally sound way to do this? We have lots of different intervention points in the nitrogen cycle. So the question is, what's the best way to do that? And people are facing these decisions in the Chesapeake, in the Gulf of Mexico watershed, in places in Florida where we're dealing with nutrient criteria and the whole management of nutrients. So it's a timely question. So here's one way that folks have been thinking about the nitrogen issue in the Chesapeake. This is some work by Melissa Birch and others that was published earlier this year. And they present the nitrogen issue using 4 different kinds of metrics. So often we would just look at this one, and this is where the nitrogen's coming from. So there's some of it going into Chesapeake Bay is coming from the atmosphere, some of it is coming from land use, and some of it is coming from direct sewage input or wastewater treatment input into the bay. So that's the relative importance of those different sources, just from the amount. But if you look at the impacts of those sources, if you tie the source to the impact, you see a very different picture. And the second bar here is mortality associated with asthma and other respiratory issues that come from the atmospheric components. So when nitrogen is released in the atmosphere, NOx, or the NOx, and the ammonium precursors, those form particles. And some of those particles lead to ozone formation, and both the particles and the ozone are very harmful for people with respiratory issues with asthma. So it actually leads to direct issues of mortality, and the damages are strongly tied to those the human mortality and work days lost because of hospital visits and those kinds of things. So this is a whole different way to represent it. The amount of nitrogen coming in is about 30% from the atmosphere, but the damage costs that they could measure, and that's an important thing to always keep in mind. The things that they measured showed that the atmosphere actually was a big part of the problem. So we can't kind of write it off as a source. And then this is the abatement cost. So this is what it costs to fix the problem. So the abatement costs for dealing with an equal proportion of all of these sources, the abatement costs are fairly low for the atmosphere because we're dealing with point sources for the most part. Some of it's cars, but for the most part we're talking about power plants and reductions associated with power plant emissions. And so the terrestrial costs are relatively high, and the freshwater cost, which is improving the wastewater treatment plants even farther than they've already been improved, is kind of the third cost. So this is just a different way of representing the problem. And these kinds of analyses are being more and more included in the thinking for the Chesapeake work. We've been trying to do this for the U.S. as a whole. So we have information on nitrogen impacts on ecosystem services, visibility, respiratory health, crop production, damages from ozone, and then climate and UV regulation that I mentioned earlier. So what we've been doing is gathering up data on these impacts. And I'm not an economist, but we're starting to work with economists on these issues. And my metric is dollars per kilogram of nitrogen. So the damage cost, how much per kilogram of nitrogen. And a lot of these data come from that study in the Chesapeake. So in the Chesapeake, they found that per kilogram of nitrogen, about 23 and about 5 for the different air pollution components. 1.5 for ozone, and about maybe 2.5 altogether for ozone damages, and about 4 altogether for the climate and UV regulation damages. And a lot of these are based on very few data points. We only have 1 or 2 data points down here, 1 or 2 numbers. We have this is pretty well researched, and we have quite a bit of data from the U.S. and Europe on these, relatively speaking, on those components. We also looked at the impacts on freshwater ecosystem services. And things like lakefront property values for drinking water and recreation. Here we have bottled water purchases, so replacement costs. If people know their well water is contaminated, they buy a bottled water to replace that, for example. Or treatment for nitrate in wells, you would install a filter system, an RO osmosis system to reduce the nitrate or get rid of the nitrate. And then these are health costs, which came from European studies where they've looked at this issue with colon cancer and other health costs of nitrate in drinking water. And then coastal ecosystem services. We tried to gather the limited information that people have looked at where they've directly looked at nitrogen as a cause of coastal eutrophication and impairment. So here's some of the damage costs in freshwater. A lot of them were fairly small, and most of these numbers are one study where somebody looked at this. So it really is an area where there needs to be more research. But the reduced lakefront property, the freshwater services, we didn't have a good number on the harmful algal blooms. That's something where we see that in Oregon. We see places where lakes are closed for swimming because of algal blooms, and that's driven by either nitrogen or phosphorus contaminant or pollution that causes these blooms of harmful algae. And so we don't have an estimate for that. That's a low-hanging fruit for somebody to work on. And then bottled water purchases, treatment for nitrate in wells. This was the estimate from the European nitrogen assessment for nitrate in drinking water damages. Actually, the largest damage cost that we saw was associated with fisheries decline, and that was where nitrogen pollution caused all the algae to grow on the seagrass. The seagrass beds disappeared, and so the fish didn't have habitat anymore. And so we were looking at the fish and the value of those fish in those areas. And this is for the coast of Alabama and Florida where this work was done. But it's actually the highest number per kilogram of nitrogen of all the numbers that we studied was this coastal damages, and it's one value. So we need more data on this one. Just to compare them all together, this is the coastal fishing. The two largest were the air quality impacts and the coastal fishing and recreation damages. And again, there are a lot of gaps. There were a lot of things where we didn't have data for damages associated with drinking water quality, for example, and human health, or some of the recreation aspects of freshwater and coastal systems. So there's still a lot that we need to learn about these connections. But it still allows you to look at the relative importance of the different sources and their impacts. And for the most part, the damage costs are generally much greater than the cost to fix the problem or the cost to address the problem. So we have here a whole list of different abatement or mitigation costs. For example, this first one is electric utilities. That's $4.9, about $5 per kilogram, and the damage costs associated with the asthma and respiratory problems, that was approximately $30 per kilogram, so much greater than the mitigation costs. And these costs are often lower than they're initially projected. So I have another example of this later on. So we tried to just do a really rough estimate for the whole U.S., like they did in the Chesapeake, of the damage costs. And these are the fluxes. We have the fluxes pretty well constrained, largely coming from fertilizer inputs, about a quarter coming from fossil fuel combustion, and a small proportion coming from human sewage. And then these are, if you multiply those arrows by the damage cost that I showed earlier, this is kind of the relative importance. So this is the respiratory. The height of the bar is kind of the relative magnitude of the effect. This is respiratory issues. So you see that's a big one, the air quality issues. Freshwater and groundwater effects, what we know, are relatively small but still significant. And then the coastal fisheries and recreation, we need more data there, but that's also another important one. And then I tried to put what the agroecosystem benefits are, so including some of the benefits from nitrogen in this assessment. And they do this really nicely in the European nitrogen assessment that came out in May this year. But what I have is this is just basically net farm income from the USDA's records divided by the amount of fertilizer they add. So it kind of gives you the benefit, the net farm income per unit of fertilizer added. You can see it sort of falls in the middle of these different effects. So it's not that you're getting huge benefits relative to much smaller impacts. They're comparable. So that's worth keeping in mind. So I want to talk just a little bit about some of the successes in nutrient management. I'm just going to run through some of the ones that Holly Campbell and I were able to identify in our research. An initial success in nutrient management is an early one in Lake Washington, and there are many lakes where we had sewage going straight into the lake, causing all kinds of problems and beach closures and swimming issues. And that was in the 60s, actually, or maybe even in the 50s. But those point source issues were relatively quick to deal with, and the response of the lake was fairly rapid. A recovery of the lake was fairly rapid. The problem is when we're dealing with non-point source, where we can't take a pipe and divert it, or take a pipe and treat it when we have non-point sources. So in the EU nations, and especially in Denmark, they've been reducing pollution of coastal waters. And in the last 20 years or so, they've reduced pollution, nitrogen inputs to coastal systems in a number of nations by 50%. So they've really done a huge job of making these reductions. Another example of a success is the acid rain program of the U.S. Clean Air Act and the amendments in 1990 and what's happened since that time. And I'll show some examples of that. But we do have substantial reductions, about a 30% reduction in nitrogen and also sulfur, which was causing harmful effects. But a substantial reduction in nitrogen inputs to our air and water and land. Tampa Bay is a place where it's an estuary that is in recovery from nutrient additions. They were able to do some substantial reductions in nitrogen delivery to the bay. And a couple of other examples, New York's Kinesis Lake, where they brought together folks to look at agricultural BMPs to protect groundwater. And also a Nebraska study in groundwater. So this is the Clean Air Act, the results of the Clean Air Act regulations, and these are nitrogen and sulfur inputs over time. I just want to focus on the total NOx deposition over time, and you can see this is mid-'80s, and then the Clean Air Act amendments were in 1990, and you see this real dramatic reduction in total NOx deposition over this time period. And this is the projections into the future based on the current regulations and not the newest regulations. There were actually a whole host of new air regulations that were proposed by EPA in July. And so that they may actually continue to go down with that. These folks are working on those models to see what we project is going to happen in the future. But it's really clear that there's been a substantial reduction in nitrogen and also in the sulfur, and both of those together caused the problems with acid rain that I'm sure you've all heard about. And I think this is a really great way to show successes in air regulations and how we can have both reductions and cleaner air while we're also seeing an increase in GNP, an increase in vehicle miles traveled. So although we had these regulations that affected air, our power plants and our cars, we still see an increase in the vehicle miles traveled. We see these declines in the emissions of sulfur dioxide. Particulate emissions decline really dramatically, which are causing a lot of those asthma and respiratory problems. And so we can have, we can work on technologies that improve our ability to still produce power and still produce fuel, but at least the clean air part of it is, the air is continuing to, at least from these perspectives, get cleaner. We do see carbon dioxide emissions still going up, though, so that's a whole other topic that maybe one of the other speakers will be talking about in your session. And these are this is a really recent study that was done, a cost-benefit analysis that was done by folks at Columbia on the recent air regulations, clean air regulations that EPA has been working with and trying to implement. And this is one that affects nitrogen here. It's called the Crossstate Air Pollution Rule, and it will reduce nitrogen by an additional probably 20% or so. And these are the costs, this little tiny blue line, and these were the benefits that these folks identified. And so, there's a lot of data that goes into that green bar, but they certainly see for most of these, and actually for all of them, that the benefits of reduced nitrogen and reduced sulfur, reduced pollutants far outweigh the costs. So in reviewing all of our case studies, we were trying to see what were some of the common triggers for action. So what caused people to make a change, to say, okay, we do need to reduce nutrients. And so we hadn't actually seen people put all this information together before, so it was interesting to do this. And the P stands for the primary trigger, and the S stands for the secondary trigger. So for Lake Washington, it was really that you couldn't swim in the water anymore. And the recreation was probably, you couldn't swim because you would get sick if you swam in the water. So it was kind of a health/regulation issue. Recreation issue. In Denmark, they were starting to see their lobster in the area of the North Sea that they were dealing with, that the lobster were declining, and that was a big concern. It was a motivating factor for reducing nitrogen inputs into that coastal system. For the Clean Air Act, it was largely human health was the largest trigger, and also to some extent the health of northeastern forests, the effect that we were having on forests in Canada. Those were all drivers of those decisions. In Tampa Bay, it was actually related to the seagrass beds and coral areas that were being damaged, and people were, it was a big tourism and recreation issue. So there's kind of a economic and recreation link. And to some extent, it was just, they really wanted, the stakeholders really wanted to protect their bay, and they wanted it to kind of go back to what they wanted to see. And so it was, to some extent, an ecosystem health sort of issue. And then there's some of the other drivers. A lot of them have to do with drinking water, and then eutrophication issues associated with phosphorus in that case. And so we also looked at the primary sources that were associated, the sources that they reduced. And in most cases, they reduced more than one source. So that was one of the common threads, is that in Tampa they had to reduce a number of sources, and it was kind of an integrated approach dealing with multiple sources. The Clean Air Act was largely power plants and a little bit car emissions. In the Seattle example, it was purely the wastewater, so that was the point source example. And in Denmark, it was a broader range. In some of these later examples, it's actually largely based on agriculture and BMPs and working with the stakeholders and farmers to develop plans to reduce nutrient inputs to the landscape, to groundwater and surface waters. And this is just some data for Tampa Bay, showing you the great successes they've had there, where this was in the late 70s, the loading of nitrogen to Tampa Bay, and this is kind of where we are in the current years. And they managed largely by reducing the point sources. That's the big change, but they've been able to reduce some of the non-point, this is actually a point source associated with fertilizer transport, and also atmospheric depositions. They've reduced atmospheric depositions quite a bit. So even though population growth is increasing over this time period, they're managing to keep it at the same level or decreasing the inputs to the bay. So we're hoping to see similar successes in other areas like the Chesapeake, which is arguably one of the best studied watersheds in the country. And certainly there's been a lot of activity and a lot of political activity and a lot of political force behind this. But there is a TMDL, as I mentioned, a way that we deal with reducing nutrients to these water bodies, and it's a multi-state program, so it involves watershed improvement plans agreed to from multiple states. It's like 5 or 6 states here, and you can kind of see where the nutrients are coming from. It has to be a multi-state agreement, because these red areas are where the nutrients are coming from that are being delivered to the bay. So we have a lot in Pennsylvania, which actually doesn't even touch the bay in terms of directly being in contact with Maryland, Delaware, some of it in Virginia, I guess. So it had to be a multi-state solution. It also had to be a multiple source solution, because there is atmospheric component, and that's one of the reductions. There's point source issues that they're dealing with of wastewater treatment, and they're reducing those. And then they have to, agriculture is a large part of the issue, so they have to find a way to reduce agricultural inputs as well. And so that's one of the challenges that they're facing, and one of the things that the improvement plan really is causing them to take some action there. And then the other thing that's really nice is that there's a lot of data that's coming from this study and going into this, and we need to track the sources and the response, and they're looking at multiple response variables with this study. It's not just the concentrations or the fluxes. They're also looking at DO and seagrass or different habitat types. They're looking at a whole host of response variables in this process. So hope for the future, I guess, on that. Common threads of successful nutrient reduction plans. Quickly, the connection to human health and economics seemed to be the triggers, that they were either a human health trigger or a strong economic trigger in most cases. And so quantifying those factors and including those factors in the assessment and the decision is real important. Many of them were integrated approaches, especially the later cases and the more challenging cases. We have to look at multiple sources, maybe multiple different stakeholders or different groups that are producing nitrogen. And tracking of nitrogen impacts was a key part, being able to show, like in the Tampa study, we have seen this strong reduction. And they've also done equivalent tracking on the recovery of the seagrass habitat. Recognition of time lags. I think we're being forced to recognize this in many places because we're in the southeast, for example, they're reducing nitrogen loads to streams and coastal systems, but they're not seeing a recovery in the concentrations or in the bays or in chlorophyll A or anything that they want to track. And there's a time lag in many systems. Groundwater may be contaminated, and so even though you're reducing the inputs, you still have this slug of nitrogen that's moving through. Or in the southeast, they're talking about the sediments holding nitrogen. So there's a lot of things that are affecting. We sort of have to be patient. We have to build that patience and recognition of the system behavior into the study. And most of them had criteria and limits incorporated into this plan, that you had to have some sort of a limit. This is what our goal is, and this is where we want to be. And there has to be flexibility for meeting that limit. And I think the air regulations are a really good example of that, where people were allowed to sort of move things around and shift things around a bit, but still meeting that overall target. So that was one of the other critical components that we found. So what's going to happen in the future? It really depends a lot on population growth and how each individual person or collective groups of people behave. And this is from Alan Townsend. It was in Frontiers a couple of years ago. A lot of it has to do with diet. If this constant diet, this is for the U.S. So constant diet with our similar diet, I'm not sure whether they call it Swedish diet, but it's very similar to the U.S. diet with high animal protein and not very efficient use of animal protein. And then Mediterranean diet, which is more of a fish-based and less agricultural inputs. And so it really does depend to some extent, on our future choices. So this is a global perspective, and I just wanted to throw in I've been mostly talking about the U.S., but I think it's important to sort of step back and think about the global perspective. And the green bar is current 1995, and then the red-purple is 2050 projections, and this is from some of Jim Galloway and Ellis Colling's work. And this is based on current use within those regions, so current use per capita of nitrogen. So you can see we're going to have changes. A lot of these changes are in Asia that are going to be happening even more abruptly because of the huge population growth and use of resources in these areas. Some places are actually projected to go down. They're saying Europe will go down. But it does depend on how people use that nitrogen. In this case, the green bars are the same, but the red bars are everybody using North American per capita nitrogen use. So if everybody uses nitrogen at that same level, this is what we would see. And this one really jumps out at you. And so it really forces you to think about how people, individuals and collectively, we're using nitrogen, and how do we improve our efficiency, because there is enough nitrogen in the atmosphere probably to fix 1,000 teragrams. For reference, the previous one was 250 teragrams, which is 10 to the 12th grams. Sorry, thanks. So 250 teragrams, and then 1,000, so fourfold increase. There's probably enough nitrogen in the atmosphere, but it's the impacts that it's going to have are tremendous, and so that's probably one of the reasons that people talk about this issue being far beyond the bounds of sustainability. So I just wanted to talk a little bit about our personal nitrogen footprint and the role of the individual, and point you to a website that these folks have developed that allows you to calculate, just like with carbon footprint. We've all heard of carbon footprint. Well, probably this is the first site that you can look up your nitrogen footprint. And so the things that they recommend there are to support agricultural production that optimizes fertilizer use, choose a diet with less animal protein, in particular animal protein where nitrogen efficiency is not very high, and minimize fuel-heavy forms of transportation like airplane travel. So well, of course, these things are not just unique to nitrogen pollution reduction. They also would apply to other aspects of sustainability, so that's a good thing. I went through and yesterday did my nitrogen footprint, just to be perfectly honest here. And this is the average American U.S. Nitrogen use. And you can see a lot of it goes into food, consumption. And this is, they did a fair amount of research on this, but they're still testing it. So I would really encourage you to go in and play around with this and have a look at it. But the food is a big one, fuel is a big one, and then we have housing, fuel costs, and transportation, and then housing, fuel costs, and goods and services. And so mine, I don't eat as much beef as they had in this one, so mine went down a little bit. And then I travel probably a lot, too much, air travel. So that was the other issue. Mine's actually higher because of the air travel. When I put in my 6 or 8 trips a year, it's too high. And then this is goods and services were about the same. But this is the average nitrogen use in the Netherlands. So they have a little less. The total is, quite a bit less than mine and the average U.S. person. The food's a little less, but a lot of it is the transportation. So they're probably not flying around back and forth across the country to visit family and so forth. Well, the country's not as big to fly across, so they're not spending 60 hours of air travel or something. But, I just want to encourage folks to take a look at this. It certainly gives me food for thought about it was nice to just drive up here and give a talk rather than having to fly somewhere. So I'm going to just go through a few conclusions. I'm probably ready to have some questions at this point, but just some conclusions about the problem that I want you to take home with you. That reactive nitrogen has increased greatly during the last century to feed and fuel our population growth. There's multiple sources and impacts. There's many benefits and costs, and it's probably not sustainable at the global scale. Solutions involve connecting nutrient pollution to human benefits and values using easy-to-understand units. And I'm hoping that our dollars per kilogram of nitrogen is a good unit that everybody can kind of relate to, and we can build upon that. It's not. I don't think economic valuation should be the only metric, but it certainly, is a good starting point and a good part of the picture to have. Better monitoring and mapping of nutrients. I didn't talk a lot about this, but it's going to be key when we're going in and making specific plans about a particular place. We need information on what the sources are, and that information with GIS and with a lot of the mapping technologies is becoming more and more available to folks. USGS has a great tool that they have for the whole country, or most of the country anyway. And it requires EPA to work better internally and with other agencies. So this data is tracked by USDA, as I mentioned, USGS. There's lots of people tracking it, and we need to probably work harder to put that all together. And then once we recognize we need to make a reduction, we need to come up with ways to more efficiently reuse nitrogen, diet choices, more efficient fertilizer use and manure handling. That's a key component. And in talking with folks in the fertilizer industry, tractable. Restoration and conservation of natural nitrogen-removing areas, so riparian zones and those kind of areas do remove nitrogen, and that's important. We have continuing the air reductions that we currently have, and the ones that were just proposed is going to continue to reduce nitrogen inputs. And then improvements in wastewater treatment. We've done a lot to improve our wastewater treatment, but there's always improvements, and things start to sort of degrade, and infrastructure degrades, and so that's an important question. So I just want to acknowledge my EPA colleagues. I've been working with John Harrison at WSU Vancouver on some of these issues, especially Holly Campbell, who has been pulling together all the policy successes, and Dan Sabota, who's here with a postdoc with the National Research Council. And thanks a lot. Okay, not too far over.
Any questions? And please come up at the microphone.
Okay. Here, there you go.
Yeah. Thank you, Jana. It was really good to see you tonight. One of the things that you said gave the best results related to cost was the Crossstate air pollution rule. Can you speak to that a little bit?
I'll try. It's a new rule that's an extension of the Clean Air Act reductions in the acid rain program. And so that rule was proposed by EPA in the summer, and it is meant to reduce nitrogen and sulfur in a large regional area. It's mostly in the eastern U.S., but it's meant to reduce, and I think the reductions are approximately 25% of current levels, 20 or 25% of current levels. And the main driver is human health. So they went through in the proposal, if you want to look it up online, just Google the Crossstate air pollution rule, and that will show you the levels of benefits associated with hospital visits and mortality that rule is meant to achieve. So it's a new rule that they're currently evaluating. So it's proposed, but it's not implemented yet. I think I got that right. Okay, great.
So what's the cost of nitrogen fertilizer per kilogram?
That's a great question. I almost said that and I forgot. It's about $3 per kilogram. So it's on par with a lot of the other costs that we were talking about. And so one thing to think about is, some of that, probably half of that, doesn't stay on site. So in a way, it's not terribly efficient. So there could be some things to improve the efficiencies there. But that's, if you look up on the USDA calculator, it's about $3 per kilogram. There's no exceptions to this rule, I guess.
She's the boss. So you had a lot of data that you admitted was based on just a couple of data points, or one or none, and a lot of that is really important to your idea that maybe we could try to somehow quantify some of the problems. So, what kind of solutions do you have to that particular issue, or do you have none?
Yeah, I mean the solution, I guess, is that the good thing about that is that a lot of those data are fairly recent. So there's actually a lot of people working on these questions right now. I mean, a lot of the data that we used for the drinking water and freshwater work is from the last couple of years. A lot of the citations in our paper were from 2010. So there's a lot of active research in this area. So I'm hoping, if we went back and looked at it in a year or 2 years, there's actually going to be more data. And so I think part of it is people starting to look at the question and making sure that we can answer those questions. There's also a lot of research on the coastal fisheries side. There's a group at the Smithsonian that's been doing a lot of work on connecting nutrient loading to fisheries, and that work was valuable for this project and is going to continue to be valuable in the future. So I think a lot of it is as I mentioned, I'm an ecologist by a geochemist, and I'm talking about dollars, and it makes me slightly uncomfortable. I'm getting used to it, but it's a new area, and so it really does require interdisciplinary or transdisciplinary, where it requires us to talk to economists and talk to social scientists about these issues. For example, the drinking water question is something that I feel like we don't have a good handle on it, but we have here in the Northwest multiple places where nitrate contamination of drinking water is a major problem. And it has environmental justice issues in many places. So we're working with economists on that to try to get better, what are the true costs? What are people paying to or not to treat their water? Those kinds of things. So I think people are starting to look at it this way. It's starting to recognize the interdisciplinary question and working on that. But I guess the way I'm dealing with it now is just presenting those gaps, that there are gaps, that we don't have to do an integrated solution or an integrated picture, we don't have all the pieces yet. So I'm hoping that with an assessment you can say, here's most of it, and see what folks think. Because sometimes we do have to, the folks that I work with at EPA that are on the decision-making side, they have to make decisions. So they may not have the perfect knowledge, but we're moving in that direction. So that was a long answer to your question, but thanks. That was a good question. Hi.
Hi. Thanks for your presentation. I wonder, is there research in the Willamette Valley about the width of riparian buffers that are effective at reducing nutrient loading into streams?
Yeah, there's actually been some work by Jim Wigington at EPA looking at riparian buffers. And some of it is the width, and some of it is just the dynamics of the groundwater. So if the width issue assumes that the water is going to be passing through the riparian zone, the agricultural runoff, for example, is going to pass through the riparian zone and go into streams. And it works like that in a lot of places, but it may be a little more complicated in some parts of the Willamette. So the riparian buffers are certainly important, and there's actually a number of different projects that folks are doing. We're doing some of that work as well to look at just how much nitrogen is moving around and how much gets into streams. But that's been the issue, is that it doesn't always flow neatly through the riparian zone and be removed. So there may be other places in the landscape where we think about those removal sites. But I think that's part of the issue is encouraging those restoration or management so that we have denitrification places on the landscape.
So I'm just wondering about the success stories that you were talking about, and how often those solutions were regulatory, or kind of how those solutions evolved, if they were more ground up or top down.
Good question. I'm trying to think if we've really systematically analyzed them in that way. A number of them were regulatory. In the Clean Air Act obviously is. And in Tampa Bay, though, I think it was more of it wasn't necessarily a TMDL that they were dealing with, or, a process where they were told they had to do this by any agency. So some of them are not necessarily, and I know in Denmark it was more of a, we recognize the lobster habitats declining and the lobsters are declining, and the community really focused on doing that. It wasn't necessarily a regulatory solution. So it's kind of a mix. I think that having a limit or a criteria was a critical piece in all of those, but that didn't necessarily mean that that was an imposed limit. But that's a good question. We should probably go back and look at that more carefully.
Talked about supporting agriculture with optimal nitrogen fertilization usage. How would you go about identifying that type of agriculture?
Well, there are, I was going to have a slide on this, I guess. There are actually a whole host of different things that folks are currently doing. Some of it has to do with the way that we use manure and treat it and cap it off so that it's not releasing ammonia or N2O. That's certainly one of especially ammonia. Those are some of the practices that folks are talking about, and balanced. So some of the things that I've read just very recently, balanced fertilizer, making sure that you have the right ratio of different nutrients so that nitrogen's used most efficiently, the timing, precision agriculture, so that you kind of know a little bit about the soils ahead of time, so you're applying more to places that you think are, needing more fertilizer, and the timing and the placement. Oh, yeah, that's a really good question. I wish I had the answer to that. Yeah, it's something that we have a little tiny piece on in the paper that we're working on now, that there needs to be kind of pressure to ask for that. Just like in sustainable forestry, there's a lot of pressure to identify woods that were harvested sustainably, for example, at Home Depot, for example. We probably need something similar in the food consumption side of things, or we don't have something. I guess I shouldn't say we need, but we don't have anything like that, and that would, organic is part of it, but I think there's also, somehow identifying sustainable practices is an area that is real rich for opportunity. One that pops out would be pasture needs versus. Yeah, yep. That's a good point. Yep. Yep. Any other questions? I'm just looking. Well, yeah, thanks a lot, everybody. I really appreciate your attention and time, and it was fun. Questions?